Welcome back, folks. So we've got here another example where we're going to go ahead and calculate what the intervals are where this function is concave up and concave down. So this one's maybe a little trickier than the previous one to guess from the picture, because we can see it's sort of concave down over here, and it's definitely concave up over here. It's maybe a little tricky to guess exactly where in here it is that it switches concavity. So I'm going to show you how to figure that out for this function. All right. So first up, we need the second derivative of this thing. So we have to first take the first derivative. Okay, so it's the derivative of the first, which is 1 times the second, which is e to the minus x, plus the first. But note, to take the derivative of e to the minus x, I need to use the chain rule. So I'm not going to spell out the whole chain rule, but make sure you're using the chain rule here to get this minus 1. So you can go back and double check that if you missed that this was a chain rule. Okay, so I'm going to rewrite this out so I can simplify it before I go ahead and take the next derivative. Minus x times e to the minus x minus e to the minus x. So note this and this term cancel. This is going to be minus x times e to the minus x. And that's just the first derivative. Okay, so we need to do the second derivative. So we need to take the derivative of this. Okay, so again, this is going to require the product rule. So minus 1 times e to the minus x plus minus x times, and then the derivative of e to the minus x, which, as before, by the chain rule is this. And so this is going to work out to be minus e to the minus x plus x times e to the minus x. And then I want to factor this. So this is e to the minus x times, and then minus 1 plus x. Okay, so here is our second derivative. And now we want to figure out where this function is concave up, where this function is concave down, and where this function changes concavity. And here's where things are going to end up working out very much like what we did with the first derivative test. Namely, when we look at this and we want to know where the function could possibly change concavity, well, since concave up means positive derivative and concave down means negative derivative, the only way a function can change from concave up to concave down or concave down to concave up is if the second derivative goes through 0. So the points I'm going to look for are the spots where the second derivative is 0. Okay. Now, as has been a recurring theme throughout the course, this is never 0. Okay, and this is 0 when x is 1. Okay. So I'm going to go ahead and make myself out a little number line. And so the only place that this function can change concavity is at 1. Okay. Again, looking at the graph, I can see that it's concave down on this side and concave up at this side. So when we eyeballed this before and said, hey, it looks like the inflection point's about here at 1, in fact, it turns out it is exactly at an x-coordinate of 1. Okay, so if we wanted to write down the inflection point here, write down that the inflection point is 1, comma, and then g of 1. So you have to go all the way back to what g was, and so it's going to be 2 over e, or 2 times e to the minus 1, whichever you like, for the inflection point. And if we want to write, okay, so where is it concave down? It is concave down on minus infinity to 1, and it is concave up on 1 out to infinity. Okay. So again, there's a lot of different ways you can communicate the information that we've found here, and the question might ask for various combinations of these things. All right. Until next time, be well.